Did my professor?
Hey guys, welcome to my, oh wait, no, wrong video. Hey guys, welcome to BME 205, day 1 of 28. Good afternoon. Okay, let me just admit everyone in. I'll change the settings so we don't have to do a waiting room every single class. Today may be the only day that I'm on time for lecture.
Fantastic.
Let's see. At first, I thought I had 28 in this class, and then the count went up recently. All right. Labs won't start for a while. And the labs, there's actually this year. So, okay, let me actually back way up. I'm gonna share my screen and show you guys the syllabus before I get into how the remote learning aspect affects the format of the course this semester. Okay. So the course is active on Blackboard. You can access the syllabus. You can also access the course slides for all lectures. There will be 10 lectures. There's actually an 11th lecture, which this is my 6th time teaching, and I've never once gotten through all the material. Who knows, maybe it will happen this year. But it's not likely. So this is a introductory course on circuits. The syllabus is here and also on Blackboard. Oh, people are flying in from everywhere. Let me just make sure everyone's out of the waiting room. I'm sharing my screen. Hold on. Okay, let's see if there's anyone in the waiting room. Doesn't look like it. All right. I think everyone's in. Try again. So this is a 4-credit undergrad course that all BMEs take in their second year. You can imagine what the objectives are. It's to familiarize yourselves with concepts in electricity that apply specifically to the study of the body, biomedical engineering. And so we cover both DC and AC circuits. If you don't know what those are, worry not, we'll cover that. There is a lab component to this course, and usually the way the course worked was, well, for the first month, it's all lectures because it's difficult to do a lab without some requisite knowledge. However, usually about a month into the course, on Mondays at 3 o'clock, you guys go to the lab, which was in C51 Steinman, and you perform a circuits lab with a breadboard and circuit components and some measurement tools. However, this year, obviously, we are not able to do that. And so the solution that has been worked out for this another lab courses is that you will be getting a kit, a circuit kit, um, distributed to you. And of course, this brings about the challenge of how do we get these kits to each and every one of you. And so maybe what I'll do now is I'll do my first poll. I like polls. It seems fun, although I find them pretty finicky. We'll try to make it work. Please, hold on. So the reason for this poll, if I can make it work, which I don't think I can, because it's already giving me fits. Let's see. What I'm trying to figure out is, are you all located in an area where the kids can be shipped to you? Or are also a related question is, are you located in an area close enough where you can make a one-time visit to campus and pick up the kids? I don't know which option within the United States or Canada. Multiple choice. True. Okay. See if I can post this now. Save. Oh, I managed to get it to work. So the reason is we have to ship these to you. And I know that there have been, we already have one person who's outside of the US and Canada. So there you go, 2 people. And so this is going to be, I don't know how, and that's the thing. I don't know how we're going to get kits to everyone. I mean, I guess we can do international shipping. Is anybody in like rural Poland or something, like somewhere where we can't possibly reach you? I don't know. You don't have to disclose
Yes.
location in public. I am in Poland. Oh, I was just fucking around. I mean, I was just messing around, and there actually is someone in Poland.
Jeez.
I am Polish. That's why I use it as an example, because, okay. So yes, and the issue is I don't have all the kits. I have all the breadboards, but I don't have all the components yet. So there's 2 parts to the
No.
laboratory equipment. There's the actual breadboard. By the way, all this stuff has to be returned because this is not cheap. We need to reuse it for future versions of the course. But see, I knew that this was going to be an issue. I knew that during the pandemic, there are students that elect to stay overseas. And so we are going to have to find a way to get everyone these kits. Now, the good news is that I'm going to go back to share my screen. The good news is that because the course is being done remotely, we are no longer constrained to these hours for the lab. I am happy to have the TAs arrange pre-recorded maybe videos to show you how to actually carry out the labs, and we're all going to have office hours that you can access myself and the 2 TAs for help. However, there's no more, you have to be out of the lab by 5 o'clock, right? You can, especially if you're in a different time zone, there's no reason why you shouldn't be able to do the lab whenever you want. So the only thing I care about in this course is that you learn the material, and how you learn the material, I'm pretty agnostic to. And so if you elect to, yeah. So what I'm trying to get at is I don't want to have scheduled lab hours for this course. I don't think it makes any sense. First of all, everyone works at their own pace. Some people, when they receive their kits, will want to get started right away. Some people will wait till the last minute, and that's, I want to respect everyone's preferences. And so, and also, I'd rather not use the scheduled Zoom time for labs because there's so much material to cover in this course that I think it'd be wasteful to use the whatever 4.5 hours of Zoom that we have every week on the labs where you could very well be doing them as homework assignments. Like I said, we have 2 TAs for the course. They've both taken the course, and they will be excellent resources at helping you through the labs. I also think that this format, the fact that you get your own equipment to have at home, is way better for your learning, because you have it 24/7. You can spend as much time as you want in building your circuits. The other thing to note is that the difficulty of labs is not high in this course. We're just trying to get you to learn how to measure a voltage, measure a current, connect resistors in series and in parallel, do a basic frequency sweep. Trust me, the lab component of the course is not the most challenging. And so the labs, again, they're going to be at-home labs, and I will coordinate with the TAs the shipment of the kits to your home. So you will have to provide a shipping address where you will be able to retrieve them. And if there's anyone that feels that they are in a location that may be hard to receive a shipment to, please let me know right away, and we'll work it out. But in theory, it should all be possible to get everyone a circuit kit, and I'll tell you, don't email me the address because, yeah, that's okay. We're not going to use your CUNY first for this. Don't worry. There will be an announcement on Blackboard soon, which will instruct you on how to provide your mailing address. And again, I think this is cool. I think that it's cool that you get your own. I've seen the equipment. It's very modern. It's all connectable to your computer via USB. It's just a much better way of learning circuits than the antiquated way of walking into the basement and finding some breadboards and some resistors and hacking at it for 2 hours. I think this is going to work much better. We will have office hours, both myself and the 2 TAs on Zoom, obviously, but the day and time has not been announced yet. I've asked the TAs to post their office hours on Blackboard. I will also post mine. I'm trying to wait to see how, in the past, there's been overlap between my office hours and the other courses that you guys are taking. And so I want to make sure that I find a time that is going to work for everyone. But you will have access to myself and the TAs. You all know the prereqs. There is a nominal, this is a non-zero textbook course. You don't need a textbook. However, lots of students obtain a textbook as a supplementary learning tool. And here's the information that you need. The author, title, and publisher. Many of you are resourceful and can obtain this textbook. That's all I'll say. So, if you are in a situation where you really want this book and you can't afford it or something, by all means, reach out to me. The book is good for practice problems. The backs of the chapters have practice problems. I will do my best this year to not use those practice problems for the actual exams, homeworks, etc. Although I must admit that making new questions for this course without making it too hard or too easy is not as easy as one would think. The topics. So the first half of the course is DC circuits, stands for direct current. We cover basic notions such as voltage, current, resistance, series and parallel connection, and some theory for how to simplify circuits. The second half is on AC circuits. So AC stands for alternating current, but really what it means is that the quantities that you're measuring are varying with time. So AC does not necessarily mean sinusoidal. In many cases it is, but it doesn't have to be. It can be anything that's not static. So DC just means static, which means that if you analyze the circuit, the solution that you get will apply to all of time, right? So you're just looking at a static system. On the other hand, AC just means that there's a temporal dynamic, which means that these quantities, they vary with time. We do get into some amplifiers. Op-amps stands for operational amplifiers that are very applicable to bioelectricity. So the body generates electricity in certain organs, such as the heart and the brain. Those are heavily used in medicine for diagnostics. So if you've ever had an EKG or an EEG, maybe even, then you have had your body's natural electricity measured for medical purposes. And so given that you're all in the biomedical engineering program, we try to tailor the material to those concepts that are most applicable when dealing with bioelectricity. Oh, someone's already posted the link. There you go. I do not condone this, but of course, like I said, Pakistan. Okay. Oh, oops, sorry. Direct message. Yes, there's no problem. Asia should be no problem. And again, I know that there are very good reasons for why many of you or some of you are abroad. We've had students during the pandemic because of visa issues are staying abroad. So like I said, everything will be done to make sure that you will get the circuit kits. Okay, I will do everything in my power. That we obviously the department has funding available to cover all the shipment costs. So we want to make sure that all of you have a chance to do the labs. So instructions for that will follow. The stuff that you guys all care about is how you get evaluated. So there is a midterm and a final for this course. There's also a set of homework assignments and usually about 3 labs. And the 3 labs this year will not really vary that much from homework because you're going to do the labs at home on your own time. And so, you'll have about 10, between the homework and the lab, you'll have about 10 mini projects to carry out. Now, first thing I usually say about the homework is that, do your own work. You're absolutely allowed and even encouraged to discuss solutions with, amongst yourselves. Especially, I have a daughter who's in her first year of college, and I know that she, they have ways of organizing themselves online so that they can emulate some sort of a social component to online education. I encourage you guys to do the same. There's nothing wrong with working together when discussing the homework problems. However, when it comes down to actually writing out your solution, you must do so yourself. So you must sit down and write out your own solution, not copy the solution from your colleagues.
So,
Yeah.
yeah, speaking of that, do you want like if everybody in the class agree, I think we can like set up a Slack channel or a Discord channel so everybody can like join the channel and work together. Like if any, like if someone has a question, they can just ask the question, and if anybody else know the answer, they can just answer that really quickly. I think we did that last time.
That's a great idea. I think Slack is a great way. That's Sam. He's one of the TAs for the course. And I think a Slack channel is a great idea. And I encourage you guys all to use any medium that you feel comfortable with to discuss the topics in the course as well as the homework itself. Now the issue of exams. So, online exams, I'm gonna stop sharing my screen. There's the issue of plagiarism, cheating. That's not even plagiarism, it's just cheating. So I've kind of dealt with both sides. What I mean by that is I've had students that have cheated on final exams, and it's made for very uncomfortable situations that took way too much of my time. So academic integrity is for me very important. I'm very easygoing, but I feel strongly that if an institution is graduating someone from an engineering program, they are vouching that that person has a certain set of skills, and there are all kinds of stories from the history of engineering, bridges that have collapsed, etc. And I really believe that academic integrity is important. I'm much more relaxed kind of on other issues philosophically. This is awesome. So I've also had students come to me and say that they don't like that other students in their class are cheating and they are not, right? And so I think that sticks with me more than anything else, because that is one thing that I really wish that I did more, because I in a sense I feel worse for the student that is doing their own work, putting in hard work, and comparatively not doing as well as other people in the class that are taking shortcuts. So it's very difficult to prevent cheating during online exams. Students are very creative, and there's no matter what software comes out, short of, I don't know, very sophisticated eye tracking, me showing up to your house sporadically while you're writing the exam, there's just very little that can be done to really make sure that you're not cheating. And at the same time, I don't want to insult anyone by insinuating that I think you guys are all cheaters. And so it's a very difficult thing to balance, to determine what is the right amount of scrutiny such that the evaluation of the course is fair. And so an idea that has always appealed to me is oral examinations. What is that? So when I was a kid in Poland, this is how I was tested. You would, at the end of the year or whatever, you go up to the front of the class and you have a little conversation with your teacher. And the teacher basically grades you based on that conversation. Yeah, it's not ideal, right? Yeah, obviously you can see how it could be subjective, right? I mean, especially if you don't hold on. I want to I want to do another poll here, but I don't know why Zoom makes polls. Yes, I do. No, I want to end this. Don't do that poll again. I'm trying to figure out how to make a new poll. I'm really curious as to how you guys feel about oral exams, and I may not be able to. Hold on a second. Give me a second here to try to figure this out. See if I can do it now. I don't know this. Okay. Okay. Give me 1 second. All right. Let me see. Ugh. Is there 2 questions? I can't tell. If there's a second, you don't. Yeah. I don't know if the second question made it to the. I don't know why Zoom has such a hard time, or gives me a hard time. Oh, there is a second poll. Hold on. Poll 2. How do I launch poll 2? This could be such a good feature if they just worked out the bugs. Oh, here we go. I figured it out. All right. I'm really, and there's no there's no right answer for this. I obviously want to hear how students feel about it, because it is, as far as it's the only way that I know of that would at least make it very hard to cheat. Like, you know, sure, there'd be some, like, some people could communicate, you know, as soon as they leave the exam, but you know, okay. The other thing about the online, verbal examinations is that it is potentially advantageous to students that are that have a, you know, that have a learning style that differs from what is typically tested for in school. Like, you know, the way we're evaluated is, you know, you have to be able to read a question on a piece of paper. You have to be able to solve that question as quick as possible and then write down the answers. And not everybody learns that way. Like, the you know, the greatest philosophers, Socrates and Plato, they didn't have to write anything, right? They would just talk, and they had scribes that would write their thoughts down. And there's probably a lot of people out there that are like that. They're you know, I'm not an education specialist, but I know that there are people out there that excel in these kind of discussion format. And so for them, the oral examination would actually be great, because, you know, the amount of hardcore math they have to do would be minimized, right? I'm not going to ask you to solve differential equations. I'm gonna test your knowledge. So we have, most of you are in the middle category, and then 8 of you don't like the idea, and 5 of you love the idea. Okay, that's pretty good. So I actually don't know. I'm going to talk to the other faculty in the department, and I also maybe also. So first of all, is there anyone, I'm happy to let you guys comment on not just the topic of verbal examinations, but in general, how do you guys feel about examination format during remote learning? Okay. Yeah. Yeah, I mean, for sure, interviewing. Yeah, I mean, there's definitely lots of, what I always tell my graduate students, yeah, I hear you. So what I always tell my grad students is that um, good technical skills are obviously important in engineering, right? But they're equally as important are good communication skills. So the difference, like if in a company, the difference between um, a technician and a manager are usually just the communication skills, right? And some people, of course, they don't want to be managers, and that's perfectly fine. But a lot of people want to climb the ladder, and so really, what separates people in companies is your ability to communicate your ideas. And so that's one thing. And same thing in if you go into academia or the public sector, your ability to communicate your ideas is super important. And in a way, it's harder to learn because you're not. We don't teach you how to do it. You have to learn it on your own, which is harder. You're learning it in an ad hoc fashion. And there's a lot of skills, like to be able to compose yourself, to be able to put yourself into the standpoint of the audience, to know your audience, to format what you're saying to your audience, and to speak concisely. These are all things um, that go, these are the ingredients of being a good communicator. So actually, I have not worked out how I would actually do it. You know, I would, so what I would need to do is come up with a list of questions that can be answered, objectively, that leaves little room for me to interpret what you're saying, right? Because I mean that's the potential downside of oral examinations, is that there's a disagreement um, between the instructor and the student on comprehension. We want it to be crystal clear whether or not you answered the question correctly. Yeah. Anyways, I think it's a very interesting idea. What I may end up doing is like having one of the exams be written and one be verbal. I may end up having both be written. I probably will not do both verbal because, the last question is exactly right. We would have to work out beforehand, which the problem is, like, usually I have it, like when I grade exams, I try to make a list for every question for what I need to see to get you the points. And then oftentimes you get into gray areas where a student definitely had the right idea, but didn't use the exact right term. There are no quizzes. If we had quizzes, our workload for grading in this course would just be astronomical. So exams are a big percentage of the grade, and that's why it's so important that we evaluate people in a fair manner. Because at the end of the day, it's difficult to enforce integrity for the homeworks in the labs, and so the exams have to be worth a lot. And my goal is to make sure that that we grade you guys fairly. The grading for the course is, I'm not gonna all of a sudden let's just hypothetically, we implement the verbal examinations and everybody bombs it. I'm not gonna give everyone in the class a C, right? Obviously, in that case, I would scale everyone's grade up. Yeah. So don't worry, at the end of the year, if there's 30 of you, whatever, 7 or 8 of you will get an A, 10 of you will get a B or something, whatever. Like this, it's not my methods for evaluation are not going to change the final distribution of grades. Okay. So there's no final verdict on this yet. In the past, the exams have been, so I can't remember last year whether COVID started before or after the pandemic. I know that the final exam was obviously at home online, and you have to turn your webcam on. Other professors have done things like you have to point your webcam on your piece of paper, and I have to see your hand and your pencil writing. So again, it's not a perfect solution, but it is a solution. And again, if you guys have ideas for how, oftentimes students are well suited to giving us feedback for how we can make this remote learning experience enriching, fair, and enjoyable for everyone. So if you have ideas, by all means, feel free to suggest them. Okay, I'll just finish up the syllabus and we'll start with the material. I think that was basically it. You do have to come to class. Although last semester I took attendance. I haven't decided whether I'm going to do it. I gave people points last year for just showing up, which I may or may not do. Video is encouraged, first of all, from my standpoint, teaching to a bunch of black boxes is no fun. But also, it just makes it feel much more real if we all get to actually see each other. But I understand, I'm in my 8-year-old's bedroom right now, and I understand that many of you may not want to expose what your background looks like. So I get it if you don't turn on your camera. I'm not going to penalize you or anything like that. But it does. I think it does enhance the oops, stop sharing, sorry. It does enhance the experience for everyone if most of you have your video on. All right, is there any questions, first of all, before I start on the content? No? Very quiet? Okay. All righty. We will begin. So the good news is that today's lecture is very, very, well, I don't want to say anything is easy, but the conceptual difficulty of the material is not high. Okay. So on Mac OS, there's some kind of a weird, well, it's a bug, it's a glitch that happens when you're sharing your screen via Zoom and you have a slideshow going on PowerPoint. So what I will try to do is not avoid I will try to avoid the slideshow. And if any of you are having a hard time seeing what's on the slide, let me know and I will turn the slideshow. But I like to be able to annotate my slides as I go. And so I prefer not to turn the slideshow feature on. Now, all the slides are already posted. So you are encouraged, you're asked to read the slides ahead of time. Also, it doesn't have to be, I mean, ideally ahead of time. That's what I always tell my daughter. She should always read her material before the lecture. Otherwise, it makes following some lectures very, much more challenging. And what that means is, especially this year when we are remote, is I'm gonna try to limit the amount of reading that I do from the slide, right? So I've heard my daughter complain about professors that come up here and just start reading from the slide. So I'm gonna try not to do that. I'm gonna try to just hit on the important concepts. And so everything that's in the slide, you're responsible for, but I will try to give you something different. I will try to give you something different than what's on the slide, something more than what's on the slide. Yes, I do post, I record these and I post them. And I think that's one of the best things about the remote learning is that you can watch, you can rewatch, you can binge watch the 205 lectures. If you're ever having insomnia the night before an exam, it's scintillating stuff. Okay, we will launch into the material. So again, this is lecture 1 is an introduction into the basic concepts underlying electrical circuits. So first of all, why do you as BMEs have to learn about circuits, right? Maybe some of you are going to end up working, in the, more in the orthopedics or microbiology kind of setting. So why do you need to know about electricity? Well, there's a couple of reasons. One is that, there's certainly a sizable section of biomedical engineering is related to, medical devices, bioinstrumentation, which are electrical by nature. And so I mentioned, 2 of the biggest kind of applications, the heart and the brain. They're both essentially electrical systems, and they can be recorded and stimulated with electricity, right? So if you think about a pacemaker uses electricity to entrain the heart rhythms. So entrainment is this idea that if you stimulate the heart, and actually I don't actually know that this is how they work. I'm more of a brain guy. In fact, I am a brain guy, but I think I know how pacemakers actually work. You send in pulses of electricity into the heart, and that exogenous stimulus ends up makes the heart pulse at that desired frequency. So if you have an abnormal heart rhythm, you can come in with an external device that basically corrects it. And that's called entrainment. Is this idea that you have an external pulse or sinusoid that ends up transferring that rhythm onto the target organ, in this case, the heart. And the brain works, does what it does by cells communicating with one another using very short and very weak electrical pulses. And so those can be measured either by inserting sensors into the brain, via surgery, or non-invasively with something known as EEG, electroencephalography, and ECG stands for electrocardiogram, right? In both cases, you can interact with these organs both by just passively measuring their electrical activity, or you can actually put electricity into them to try to get them to behave in a more desirable way. But even if an organ or a system is not electrical in nature, you can still use circuit theory. You know, circuit theory, it's really, you can think of it as an input-output system, and the nature of that input-output relationship is governed by the architecture of the circuit, right? So the circuit theory is used for more than just modeling and measurement of circuits. So, you know, for electricity to flow, you need there to be a closed path, right? And so the basic idea is you have some separation of charge. So what a battery does, as we all know, is it separates positively and negatively charged matter, and then those positive charges, whether it's electrons or charged molecules, they travel from one terminal to the other, right? And the reason that this happens is because there is less resistance along this path than there is from here to here directly, right? So you need to have a barrier in between these two poles in the battery. You need to have an insulation of charge, right? So something that you'll hear me say a lot in this course, perhaps too often, is that current follows the path of least resistance, right? So if you have some positive charge here and some negative charge here, why doesn't it just travel from here to here directly, you know, through the battery? Well, the reason is the resistance between the two poles here is huge, bigger than the resistance along the circuit that contains the battery, sorry, the lamp. And so the current, seeing that it has a lower resistance along this path, takes that path and lights up the lamp. And so how does that work? Well, the electrons travel through the filament, and energy cannot be destroyed, right? Conservation of energy. The energy has to be transferred some way, and that way, in this case, is by the emission of light and heat as well. Okay, so you need a closed path for charge to flow. So here is the circuit that you will have to build next week. Just kidding. This is the circuit for a radio receiver. It looks complicated, but it is our hope that at the end of the course, you will have the tools and techniques to be able to deconstruct this circuit and figure out what the various modules are doing, right? So you have the things that I will point out here is that you have an antenna. So that's it's a circuit element that listens to electromagnetic radiation and transduces that into a current along the wire, right? And at the other end somewhere, you will have a loudspeaker, which is just a membrane. So a loudspeaker is basically a membrane that vibrates, and the vibration of that membrane produces sound pressure waves, which travel to your ear, right? So the auditory output is here. I think it's high now, but this is the loudspeaker basically output here. So you need a front end that listens to the radio waves, and you need a back end which, you know, emits the sound so that you can listen to it. And I suspect that many of you don't use radios anymore, but maybe one of these years, you know, we'll replace the circuit with something like, here is the circuit that's located in your smartphone. Okay, moving on. So what does it mean to solve a circuit? I mean, strictly speaking, you want to be able to know what the voltage and current is at every point of the circuit. But another way that we analyze it is just to characterize the relationship between the input and the output, right? So circuits often have a node that serves as the input. So there's a voltage that plugs in there, and they have an output. So that's a node where if you're a user of that circuit, you will plug your device in there, right? So the wall outlet, you can think of that as an output, right? You plug in your device into the wall. Behind the wall is the circuit, and your device is the consumer of that circuit when you plug it into the outlet. So today we're going to be covering the basics: charge, current, voltage, and power, right? I'm not going to spend any time on the next two slides, other than to say that make sure that you are familiar with the standard units for current, which is the amp, time, which is the second. I don't think I need to really unpack that at all. So current is measured with amperes. So current is, as you'll see, charge per unit time. Voltage is the amount of energy per unit charge, and I'll explain that in just a second. Resistance is the ratio of voltage to current. And then we'll also introduce later in the course, in the second half, the notions of capacitance and inductance, which are less accessible, but also very important to understanding AC circuits. Make sure you know your prefixes. You know, it breaks my heart when students lose points on an exam because they weren't able to convert from milliamps to amps or something like that. So just make sure that you know these. That's all I'm gonna say. They go up to, it's interesting, when I was a kid, memory was measured in kilobytes, and now we're already up to terabytes, and if you're working on big projects, you get into petabytes. So I think they're gonna eventually have to add new prefixes. That's all I'm gonna say about that. Charge. Okay, so opposite charges are attracted to one another. This is like a fundamental property of the universe. And so the idea is that if I apply a force and I separate, so if I have a positive charge next to a negative charge and I somehow pull those charges apart, right? To do that, I need to be applying energy, because when two opposite charges are separated, that is a form of potential energy, because if I let go, they will, again, be attracted to one another and they'll move towards each other. And so to me, voltage is the act of pulling apart, unlike opposite charges, or the act of squishing together two like charges, right? So these two like charges are repelled. Again, this is a fundamental axiom. You just have to take this for granted. And so again, if I want to bring these two charges together, then I have to apply energy. And if I want to separate these two charges, I have to apply energy. And the amount of energy that I apply is called the voltage. Right? So that's what voltage is a form of potential energy. And that is I think voltage is kind of the harder concept to understand, because I think we can all visualize flowing charge past a point, and we can kind of intuitively current is. But voltage is a little bit more abstract. So that's why, again, voltage is the act of pulling these two charges apart. And the more and the stronger I pull them apart, the more voltage I'm applying. And when I let go, the faster those charges will move back to one another. So that's my explanation of voltage. Yeah. How to measure charge. So we know what charge is. You know, it's a molecule that has an imbalance of protons and electrons. And the units of charge are called coulombs. So a coulomb is a huge amount, 6.24 times 10 to the 18 electrons in 1 coulomb. And therefore, in the lab, we deal with very small amounts of coulombs, so pico, nano, or micro coulombs. Okay, so because electrons are discretized, these are quantum phenomena. The only charges that can occur in nature have to be multiples of 1 over this, right? So if one electron has this much charge, it's not possible to have fractional amount of electrons. And so all measurements of charge, by definition, have to be integer multiples of this fundamental quantity. I've already mentioned the conservation of, I mentioned the conservation of energy. There's also a conservation of charge, right? So charge cannot be created or destroyed, only transferred, right? So you cannot make an electron disappear, but you can make it move from one atom to another. And so the algebraic sum of the electric charges in a system, whether that system is your little breadboard or the universe, is the same. All right, so we know that charge can flow. When it flows, we call that a current. So charge is current is the amount of charge flowing past a point in 1 second. Now listen, one thing that confuses a lot of people is that we take a convention in this course, but in general in circuit analysis, where we assume that it's the positive charge that flows. That's actually the opposite of reality, but the good thing is that it doesn't matter. So in the circuit here, we assume that the positive charge is traveling clockwise from here all the way back around to the negative pole. Now, in reality, it's often in conductors at least, it's electrons that do the traveling. However, it is the statement that there is I amperes flowing clockwise is equivalent to saying that there's negative I amperes flowing counterclockwise. And that's why it's perfectly fine to just pick a convention and stick to it. Right? And so in this picture and in every circuit that you deal with, you will assume that it is the positive charge that does the moving. Okay. And that's basically a universal convention. Okay, I think this is our first equation of the course. It's very straightforward. So we know that current, and hopefully this is a review of high school physics for most of you. Electric current is just the temporal derivative of charge. So again, another way, so all this equation is actually saying is that if you, for 1 second, if you kind of put your charge meter on a piece of wire at that point and you count how much charge went past your point, that is your measurement of current. And so the units of current are coulombs per second, which is known as the ampere. So 1 amp of current is an amount where 1 coulomb of charge travels past a given point in 1 second. So that is a very large amount of current, by the way. 1 ampere is dangerous to the body. So when we apply currents to the body, we generally apply them in the order of milliamps. And if you want to do something like, if you guys have ever heard of shock therapy, also known as electroconvulsive therapy, where we are actually trying deliberately to induce a seizure, there we're talking about, in the current order of an ampere. So an ampere is a very large amount of current, at least as far as the body's concerned. So hopefully you remember from calculus class that if you integrate both sides of this equation, you arrive at an expression for the charge as a function of current, right? So if you integrate the current, you get the charge. And again, pay attention to the integration limits. Q is the amount of charge that has passed through a point between time points t0 and t. Okay, this is an important slide in the sense that it presents definitions that are kind of used throughout the course to delineate the course material. In fact, we have direct current, which is really another word for saying everything is constant. So every quantity in a DC circuit is static across time. An alternating current, so the way that this is taught in high school is that the current goes one way, then reverses, then goes back. Really what they're trying to say is that the current is sinusoidal. So the current, in your home electrical systems is sinusoidal. It gives me a chance to ask the first question in the course. At what frequency does current vary in our electrical systems that we use to run our lives? Does anyone know what the frequency of electricity is in your home? No. So it actually depends on where you are located. If you're in Europe, it's actually 50 hertz, so 50 times per second. And if you're in North America, it's 60 hertz. So that waveform has a frequency of 60 cycles per 1 second. In other words, a cycle is 16 milliseconds long. So it's quite fast, right? And so this is generally a more, I always ask the class why they think that this type of system for energy delivery is preferred over this, and I've gotten some interesting answers. So one of the reasons apparently is it's more efficient to deliver electricity in a sinusoidal way. The other reason is, for example, you're as a receiver of this current, we've all agreed upon this 60 hertz frequency, so you can listen to only that frequency with your device, and you will filter out anything that is not varying at a 60 hertz frequency. The only thing, yeah, so these are all good answers. I asked this question, but to be honest, first of all, I don't think there is a single universal answer. It is probably easier to manipulate because if you think about, this is called, another word for this is baseband. So like, this thing is just a constant, and then it switches to another constant, and then it switches to another concept. Because that kind of a waveform where you have these like square wavy type waveforms has discontinuities, right? You have these or not discontinuities, but abrupt edges. Here you have a perfectly smooth waveform. So this waveform, for example, is differentiable, it's smooth, and that has benefits to the analysis of the signal. But I also think there's a benefit to how much, how efficient it is to deliver energy across long distances. So we use capital letters in this course to denote DC current, and we use, or voltage for that matter, and we use lowercase letters to depict time varying or AC current. Another, there are many conventions in this course, so you will have to keep those in mind. So again, the convention in this course is that positive charge does the moving. And when you draw an arrow in a circuit, you are saying that positive charge is moving in that direction, right? So these two pictures are identical, right? So if you have 5 amps of current flowing along the arc, then that is equivalent to you saying you have negative 5 amps of current flowing down the arc. So these two scenarios are strictly equivalent, and you should convince yourself of that fact. It's equivalent to me saying that I walked 5 steps forward versus I walked negative 5 steps backwards, right? Those two statements are identical because both voltage and current are signed quantities. That means they can be positive or negative. Resistance cannot be negative. And we'll get to that. So our first example here. So I'm going to go very quick through this because it's very it's not very interesting. And maybe here I'll turn on the slideshow actually. So the question is this: the total charge entering a terminal is given by Q is equal to 5t times sine 4 pi t millicoulombs. And we are asked to calculate the current at 0.5 seconds. So notice that current is an instantaneous quantity, which means that it has there's a different current value for every point in time. So we know what the equation is between Q and I. Current is I, charge is Q. So what do I have to do to this function to convert it from charge to current? You have to derive. That's right. And so what law in calculus do I need to use in order to differentiate this function?
The product rule.
Yes, very good. So who wants to shout out what the derivative of this function will look like? What's the derivative of 5t?
5.
5. What's the derivative? Very good. What's the derivative of sine 4 pi t?
4 pi cosine 4 pi t.
Excellent. And when you combine that, you get, right? You get, so the first term in the product rule is 5 times sine 4 pi t. And the second term is 20 pi t times cos 4 pi t. And all of this is in milliamperes because our charge was given in millicoulombs. So differentiating doesn't change the prefixes. And so now we have to evaluate this function at half a second, right? And when you evaluate this at half a second, you get a value of, so you just simply plug in 0.5 into t, and you evaluate that and you get 31.42 milliamperes. Okay. What's the total charge? Let me just make sure that I'm, give me a second. Yeah. See if I have, it seems like the slide that has this solution is missing from my slide deck, which is very strange. Very weird. So maybe what I'll do is I'll just annotate this. I'm gonna need to find a better solution I'm gonna have to do a lot of math over Zoom, and there really isn't a great way that I've come across for doing mathematical derivations over Zoom. I think last year when the pandemic hit, I actually ordered a camera that, it's like the camera's facing down towards, is filming my desk, and it never arrived. And I blame newegg.com for that failure. But maybe I'll try again this semester to order something so that you can actually see my piece of paper when I saw these things.
Professor, can you
Yes.
like you can order a drawing tablet to do that?
Yeah, you know what? That was actually my first my first suggestion. I actually bought a tablet and I bought a stylus, and for whatever reason, in my handwriting looks bad, like even on paper. It looked atrocious on the tablet. A Bamboo. Yeah, maybe that's
Yeah, the bamboo works. It
Yeah.
should work fine.
maybe Bamboo may be good. Yeah, maybe I'll give it another shot. It's definitely useful in this course because you learn a lot by watching somebody go through all the steps. But it is no surprise that I am not, I have nothing planned for today. But this one, fortunately, the first lecture is very easy. So does anybody know if the current is given by 3t squared minus t amperes, and I want to know how much charge entered the terminal between 1 and 2 seconds? What do I have to do to this waveform here?
Take the integral.
Yes. And who can tell me the integral of 3t squared minus t?
T cubed minus t squared over 2.
Excellent. All right, so it'll be that evaluated at 2 and 1, right? So you have to evaluate this at 2. So no, sorry, first evaluate it at 1 and then subtract the result of that from this function evaluated at 2. And so the answer actually ends up being 5.5 coulombs. If you want it. I know some of you are probably super excited to solve this question. So if you just can't wait for the answer, there it is. Okay, moving right along. So as I already gave you kind of a quick definition of voltage, a more intuitive definition. So the formal definition is voltage between 2 points in a circuit, call those points A and B, is the amount of energy that's needed to move a unit charge, so 1 coulomb, from A to B. So how much energy is needed to separate 1 coulomb, right? And so the units of voltage, which are called the volts, are equal to 1 joule per 1 coulomb. So if you need, let me just clear these annotations. So 1 volt is a voltage that corresponds to, if you can separate 1 coulomb of charge with 1 joule, then you've created a voltage of 1 volt. So another thing about voltage is that, again, you have this notion of polarity. So if point A is sitting at a voltage of VAB higher than point B, that's equivalent of saying that point B is sitting at a voltage of negative VAB over point A, right? So if you flip the positive and minus poles, then you just put a minus sign here and you're still good. So if ever you're in a situation where you, for some reason, need to switch the polarity at across a circuit element, then all you need to do is just stick a minus sign in front of the quantity, right? So this picture, there are two ways of interpreting it. Number one is that point A is sitting VAB higher than point B, or point B is sitting minus VAB higher than point A, right? So this is another way of kind of, some of you may find this definition appealing. If you just switch the polarity, you just stick a minus sign in front of the voltage. And so remember, the voltage is a property of it's very much, it needs 2 points for it to make sense. Voltage is always in reference to something, right? And that's different than current. You can have current at a single point. You cannot really have a voltage at a single point. Whenever you say the voltage at point X is 10 volts, what you're actually saying is that that point is 10 volts higher than the reference in your circuit. And we'll get into what a reference is. But again, it's voltage is very much a relative measurement. You always need to have a reference. Okay, so again, these two pictures are equivalent, right? Because point A is 9 volts higher than point B, which is the same thing as saying that point B is minus 9 volts higher than point A. And this may confuse you, but again, if you find yourself confused by this notion, all you have to keep in mind is that if you can put a minus sign in front of the quantity as long as you just switch the positive and negative poles. All right. So the other reason why circuits are so important is because they're extensively used in telecommunication, right? So when you talk into your cell phone, when I was your age, before texting, people actually used to call each other. By the way, I don't miss calling people at all. I'm just saying that that's what it used to be like. We actually use something called the microphone, the speaker, to communicate. So what the phone does is it digitizes your voice and it stores it as a voltage. In fact, it stores it as a time varying voltage. And then that voltage is transmitted to whoever you're speaking to, and then recreated at their end. And that voltage on their end drives their loudspeaker, right? And that happens super quick. And the reason that electric circuits are used for communication is because how quickly they can be manipulated. And so we often use the term signal to refer to both current and voltage, right? So both of them are really a signal. And so again, and so oftentimes you'll see the word signal when encountering one of your problems. It just means a voltage or a current, basically. Whether you're communicating with a current or a voltage, it's kind of arbitrary. Okay, so batteries produce DC voltages. So a car battery will produce a static voltage across its terminals, whereas your wall outlet will produce an AC voltage. Power is an important concept. So power, by definition, is the temporal derivative of energy. But the more well-known definition of power, that it's equal to the product of voltage and current. And how do you get that? So if you differentiate, so W is a symbol that we often use for representing energy. So by definition, power is the rate of change of energy with respect to time. And you can expand that out, right? So you can, the temporal derivative of W can be written as dW over dQ times dQ over dt. right? And notice that this term here is exactly the definition of voltage. And this term here is exactly the definition of current. In other words, power is the product of voltage times current. And so, you often, your home appliances will have a power rating. And so what those ratings are measuring is the product of the amount of voltage that they're hooked up to. So for example, 120 volts, if you're talking about something like a fridge, and the amount of current that they draw, right? So nowadays we want our appliances to have low power ratings because we are trying to, minimize our energy consumption. And if you multiply power by time, you get energy. So even though the unit of power is the watt or the kilowatt, you often hear these things like kilowatt hours. So my fridge has a rating of whatever X number of kilowatt hours. That's really just a measure of energy consumption. One thing that is kind of not readily apparent is that this is a time varying quantity. So you can plot this as a function of time. So power in general has a waveform, and that's why we often refer to this, the product of V and I, as instantaneous power. So instantaneous power is the product of voltage and current at any point in time. We can also integrate that power to get energy, or we can also average that power to get average power. But in general, power has a waveform. Okay, so you can either absorb power or supply it. So for example, a battery supplies power, whereas a device will absorb power. And really, when we say absorb, it means it uses it, it transfers it to do work. And so we have another convention, and that is the following, that if the power has a positive sign, in other words, if the product of voltage and current is positive, we say that power is being delivered to or absorbed by the element. So for example, something that you plug into the wall will generally have a positive power because it is absorbing, it is consuming the power. On the other hand, if the power has a negative sign, then that circuit element is supplying the power, right? So the question is, how do we know whether to make the power positive or negative? And we know because of our, we define the conventions. So we have a current arrow, and we have numerical quantities for the voltage and the current. So let's look at this very simple circuit branch. This green box here represents a circuit element, right? And that circuit element is receiving I amperes and is sitting at a voltage of V volts, right? So assuming that V and I are both positive, the power here across this element will also be positive. In other words, this circuit element is absorbing the power, right? Because the product of I and V is positive, right? So with the way that we've drawn the current arrow, with the positive charge entering the positive pole here, the product of V and I is positive, assuming that V and I are themselves positive. On the other hand, in panel B, the positive charge is exiting the positive pole. So this pole here is the positive terminal, and this is the negative terminal. So here, the current is escaping the positive end. In other words, the product of the voltage and the current will be negative because the I here will have a different sign than the V. And therefore, we say that this element is supplying power. Okay, we're going to do some examples in just a few slides that will kind of hammer these concepts home. The only thing, if you want, you can just memorize the convention, namely that, or memorize the rule, which is that if the product of V and I is positive, we say power is absorbed. And if the product of V and I is negative, we say that the power is supplied. Okay. So we have here 4 pictures. So here, we have a positive current of 3 amps that's entering the positive end of a 4-volt battery. So in other words, we say that this element is absorbing 12 watts of power, right? Same thing in this picture, because the 3 amps is entering the positive pole of the battery, the positive terminal of the battery. So in these 2 pictures, this element is absorbing power. On the other hand, in the lower 2 pictures, this element is supplying power. Why? Because the positive current of 3 amps is coming into the bottom, or the negative terminal of this element, right? This is the negative terminal end of this element, of this green rectangular box. And the 3 amp current is entering that negative terminal. And so we say that when we multiply current of 3 and a voltage of -4, we get a negative number. In other words, this element is supplying power. And the same thing here, because a positive current is entering the negative end of the battery, of the circuit element. So another thing that I always say in this course also is that if you can trace from any one point in a circuit to another without going past any device, the voltage at those 2 points is equivalent. So in other words, the voltage here is equivalent to the voltage here, and the voltage here is equivalent to the voltage here. Right? So if you can trace your finger along any 2 points in a circuit that without going through any elements, then those 2 points are the same voltage. So energy cannot be destroyed, cannot be created. So the amount of energy in the universe is fixed. And that applies also to electric circuits. In other words, if you sum up the power of every element in a circuit, the geometric sum has to be equal to 0. Give me just 1 second and take a sip of water. Oh, I haven't taught in a few months, and my voice box is not yet in mid-season form. Okay. So another way of interpreting this equation is that the total power supplied to the circuit must equal to the total power absorbed. So you can't lose energy along the way. And we know that the energy absorbed between 2 time points is just the integral of the power at those time points. And hopefully you remember that the unit of energy is the joule. So for example, let's see, switching. Okay, so an energy source forces a current of 2 amps to flow through a light bulb for 10 seconds. And then if 2.3 kilojoules is given off in the form of light and heat energy, calculate the voltage drop across the bulb. So we have the current we have the time and we have the energy. And we are asked to find the voltage drop. So what do I have to do with these three quantities to derive the voltage across the light bulb? What's the first thing that I need to do here? There's actually a couple of different ways to do this. Anyone want to take a shot? All right, so we're gonna start you off. The total charge is given by current times how much time has passed, right? So in 10 seconds, if you've had a current of 2 amps flowing across a time span of 10 seconds, we know that 20 coulombs of charge have been, have traversed that light bulb. So now if I have charge and I have energy, what do I do to calculate voltage? What's the definition of voltage?
Voltage is a change in work over the change in time. It's the derivative of, so the units of volts are joules per coulomb. That should help you, right? It's not per time. Current is per time. Voltage is per coulomb, right? So voltage is how much energy is applied to per unit of charge. So we have this much energy and this much charge. So how much voltage do I have?
Do you need to convert the kilojoules to joules first?
You could, yeah. It'll be 2,300 joules.
So wouldn't you just make it 1 over 0.3 kilojoules and then multiply by the charge?
So actually here you can just, it's related to what you said. So you just basically have to divide the energy that's given off by the amount of charge that passed through that light bulb in 10 seconds. So that gives us 115 volts. So just 2,300 divided by 20, right? Because the two equations, so ultimately to get voltage, you need to divide change in energy by change in charge, right? So the change in charge we derived over here, and the change in energy was given to us. Okay, so to move a charge from point A to point B requires minus 30 joules. I don't like this problem because minus 30 joules is weird, but let's do it anyways. Find the voltage drop VAB if the charge is equal to 2 coulombs. So if the energy is equal to minus 30 joules and the charge is equal to 2 coulombs, what is the voltage?
Wouldn't it be just negative 30 divided by 2?
Exactly, right? So it'll be negative 15 volts for part A, and it'll be 5 volts for part B. Thank you for that. And a follow-up question, find the power delivered to an element at t equals 3 milliseconds if the current entering its positive terminal is equal to 5 cos 60 pi t amperes, and the voltage is equal to 3 times I or 3 times di over dt. So first of all, what is the equation for power?
Voltage times current.
That's right. So what do we have to do here in part A? To get a power?
Combine those equations.
Yep.
And then
And so what two functions am I gonna have to multiply here in the first part?
3i and 5 cosine 60 pi t.
That's right, right? So, so you have it all at once. So we know that the voltage is equal to 3 times this, which is 15 cos 60 pi t. And so you have to multiply 15 times cos 60 pi t by 5 times cos 60 pi t, right? Because you're multiplying the voltage by the current. And so you have 75 times cosine squared of 60 pi t. Okay, so now all that's left to do is just to substitute in 3 milliseconds into t here and evaluate this. And when you evaluate that on your calculator, you get a numerical answer of 53.48 watts. So on the midterm exam, we allow you, actually, no, it's the other way around. On the midterm exam, again, this is all assuming that it's a written exam. I don't know how this would change for oral exams. We have not let you use calculators on the midterm, but at the same time, we don't ask you to really compute anything. So historically in this course, because we want to test your knowledge of circuits and not arithmetic, not algebra. And so we've basically asked you to stop at the point where you would evaluate the numbers. So for this question, we would only ask you to get to this point that I'm highlighting here. We don't, for the sake of evaluating you on the midterm, we wouldn't actually ask you to go all the way through to the numerical answer. Okay. Now on the final exam, though, there's no way around it. You will need to use a calculator. Okay, so part B is very similar, except that the formula for the voltage is now 3 times the derivative of the current. So what we have to do here is we have to take the derivative of the current, right? So what's the derivative of a cosine function?
Negative sign.
That's right, negative sign. And that's why the derivative of this, again, multiplied by 3 is equal to 3 times negative 60 pi, right? This is the chain rule here. 3 times minus 60 pi times 5 sine of 60 pi t. And when you simplify that, you get minus 900 pi sine 60 pi t. So that's the voltage. And again, then you have to multiply that by the current. And when you multiply this expression with this current, you get negative 4,500 pi sine 60 pi t times cos 60 pi t. And then to actually obtain a numerical answer, you need to plug in 0.003 for time and evaluate. And when you do that, you get negative 6.4 kilowatts. In other words, this is since this is a negative power, this is that case where the device is supplying power to the rest of the circuit. So this will be an example where this element is providing power to the other circuit elements. Whereas here, because the power is positive, this is a case where the element is absorbing the power. Okay. Another practice problem here. Find the power delivered to the element in the last example. So in other words, I is still equal to 5 cos 60 pi t amps. If the current remains the same, but the voltage is now 2 IV. Okay, so I have my expression for current. It's that 5 cos 60 pi t. And now I'm given that voltage is equal to 2 times I. So what do I do here? Oh, I don't know what happened to my answer. I know what happened. These are the ones that I would do on the board. And I don't have a board this year. So maybe what I'll do, okay, so what I'm gonna do is be more prepared for next class. But now it now dawned on me that the reason I didn't work these out on the slide is because these are always the questions. So my system was that there's example problems and then there's practice problems. So the examples I like to do on the slide, and the practice problems I like to do on the board. And so there's no board this semester, but I will still do these, maybe not right now. It's the first day of class. We have, we have lots of time to cover these, but I will go back, probably record myself solving these with a stylus or something. But for now, I'm just going to move on. You're basically doing the same thing as here. The only difference is now your expression for the voltage, instead of being 3i, is equal to 2i. So there's nothing conceptually new here. You have an integral in the second part. So you have to know how to integrate a sinusoidal function. Okay, okay. So I like this one. How much energy does a 100-watt electric bulb consume in 2 hours? So here we have to recall our definition of power. Remember, power is energy divided by time. So if I have a power of 100 watts and a time of 2 hours, how do I convert those into an estimate of energy? Right, so maybe
power with the time.
Yeah, that's right. Yeah, we want to multiply the power by the time. So what are the units of the time that we need to multiply by?
Seconds?
Seconds is correct. So how many seconds in 2 hours?
7,200.
Yep, exactly. 70. It's basically 60 times 60 times 2, right? So when you do the multiplication, you get a value of 720,000 joules, or 720 kilojoules. And another way of saying the answer without converting to seconds is just to say 200 watt hours, or 0.2 kilowatt hours. So that's another way that sometimes energy is measured. I'll silence my ringer here. Oh. Okay. So one important distinction in circuit analysis is that of passive versus active circuit element. So a passive circuit element is one that basically just receives energy. And so when we get to them, you don't really know what these are yet, but a resistor is a passive element, a capacitor is a passive element, and an inductor is a passive element. On the other hand, an active element is something that can actually generate and inject electrical energy into the circuit. So something like a battery, right? It's a source of voltage. So anything that's a source is an active element. So an amplifier is also an active element, because even though an amplifier requires a supply, energy supply, it amplifies that. So it in a sense, it multiplies the energy that's applied to it. So it's an active element. And a generator is another type of active circuit element. Okay. So that's one distinction. Passive element is, it just sits there and it responds to
the sources of the energy in the circuit, whereas an active element can actually inject energy into the circuit or multiply it. So for now, we're going to look at the active elements. So there are two types of sources that we deal with extensively in this course. We have a voltage source, which is another name for a battery, and we have a current source. So a voltage source means that there is an ideal voltage that is guaranteed to be produced between its terminals. So this symbol means that V can be a waveform. So here V can be a function because it's lowercase v. The uppercase V means that it's a constant. So for example, a 9-volt battery. And again, what this symbol means is that no matter what happens in the rest of the circuit, the voltage between this point and this point is equal to capital V volts. Similarly, in this picture, we can guarantee that no matter what this branch is connected to, a total of I amps will flow out of this node and flow into this node. Question, or was that just someone was unmuted? I can't tell.
Okay, so what is the difference between A and B again?
Yeah, so the difference is that this can be a function, like this can be sine 60 pi t or something, where this is just a constant number. So the uppercase just means that this is like a constant battery, where this is something where it's, it can be a waveform. So it doesn't have to be constant.
Okay, thank you.
No problem. So lowercase means that it's time varying. Uppercase means that it's constant or static. So these are called independent sources because their values do not depend on whatever is happening in the rest of the circuit. Oops. On the other hand, another slide about independent sources. So, so again, no matter what happens in the rest of the circuit, you get V volts, either uppercase V or lowercase v, that is produced across these two terminals. And again, this is a time varying voltage. This is a constant voltage. In other words, this is DC voltage. This is AC voltage. Independent current source is again, I've already told you what it is. This picture just guarantees that I amps flow out of this node and into this node here. So whatever current emanates from this point has to return back to it, right? Current cannot be lost, along this path. A current cannot be lost in general, but especially not here where we are. This is an ideal independent current source. Dependent sources are more interesting. They're dynamic in that their values depends on what's happening in another portion of the circuit. And so there are 4 types, right? So we have, a dependent source can depend on another voltage or another current. And so you have 4 combinations here. You can have a voltage source that depends on a voltage. You can have a voltage source that depends on a current. You can have a current source that depends on a voltage. And you have a current source that depends on a current. So we have, 2x2 permutations. We have, so first of all, dependent sources are depicted with these diamonds. So whenever you see a diamond, that means that this is a dependent source. So to get its value, you have to analyze the whole circuit. And that applies to both current sources and, the current sources and voltage sources. Now, the way you know whether it's a voltage source or a current source, is that a voltage source will have a plus and a minus terminal, whereas a current source will just have a current arrow. And that is the only way you can tell with a dependent source. You cannot just look at the, for example, we can call this I and this V, and it would still be valid. So again, pay attention to the actual symbol of the dependent source. If it has a positive and a negative terminal indicated, it must be a dependent voltage source. All right, so dependent sources are useful because they allow us to model more complicated elements such as transistors or operational amplifiers. And so here's our first example of a dependent source. So first of all, who can tell me whether this is a voltage source or a current source?
A voltage source.
It's a voltage source. Great. And what is the value of this what is the value of this voltage source?
10I, because it's
10I.
current dependent.
That's right. Exactly. This is a current dependent voltage source. So whatever the current is flowing through element C, take that number, multiply it by 10, and that then becomes the voltage across this branch. So the way you can tell that it's a voltage source is because it has the plus and minus. Right? If it has the plus and minus symbol, that means it's a voltage source. If it has the arrow, it means that it's a current source. Okay, so there's a couple of more subtle points. Is that a voltage source will vary the current flowing through it to generate a desired voltage level. On the other hand, a current source will vary the voltage in order to produce the desired current. And in this class, we do not learn any techniques that allow us to determine how much current is flowing through a voltage source and how much voltage is sitting across a current source. So just so you know, and on any homework problem, any exam, do not try to write down what the voltage is across the current source, or do not try to write down what the current is flowing through a voltage source. We do not learn the techniques in this course to allow you to do that. Okay, last few slides before we adjourn for the day. So we are asked to calculate the power supplied or absorbed by each element in this circuit below. So maybe I'll switch to, so we have the following circuit. So we have all the voltages and currents indicated, right? So for example, how much current is exiting this battery here?
Amps.
So repeat that, sorry.
5 amps.
Right, and so when we go to compute power and we want to multiply voltage by current, what should be the sign? Should it be a positive or a negative sign?
Wait, can you repeat that?
Yeah, so we want to we know that the answer is going to be either 100 or negative 100, right, for P1. So the value of P1 is going to be the voltage, which is 20, times the current, which is 5. However, notice that this 5 amps is flowing, the current arrow, if you extend it down this
Right.
battery,
Positive.
the arrowhead will hit the negative terminal, right? And so
Right.
it's actually -5. Because the
It's a
5 amps is exiting the positive terminal. On the other hand, for P2, the 5 amps is, just give me 1 second here. On the other hand, the 5 amps here is entering the positive terminal of P2. And therefore P2 is going to be equal to 12 volts times positive 5 amps. So that's 60 watts. And P3, again, in P3, the current arrow is oriented into the positive end of the battery. And so P3 is equal to 8 times 6. So now my question to you is whether the value of, so how do we get the value of P4, right? What two numbers have to be multiplied to get P4?
The
So we equate the supplied power and the absorbed power on both sides.
Yeah, so what is the voltage across? So let's actually start off with the easier half. What is the value of the current that's coming out of this current source?
the wouldn't it be 6 amps?
Is it one?
And how did you get the 6?
Because it's because the arrow is showing the flow of current and it's on the right side of the circuit.
Right? But this current, the 6 amps that flows down here, some of it will go left and some of it will go right. So not all of it will go through this current source. On the other hand, we are told that the current that's flowing out of this is guaranteed to be 0.2 times I, and I is equal to 5. So 0.2 times 5 means that the current coming out of here is 2.5, or sorry, not 2.5, 1 amp, sorry. And what about the voltage? Now this is admittedly, we haven't yet encountered what a parallel connection is, but notice that one of the rules of circuits is if two elements have the same connection on both sides, on both the top and the bottom, then they have to have the same voltage. So notice that P3 and P4 have, they are connected by the same node on the top and the bottom, right? So again, if I can draw my finger along any points, any 2 points, it means that they're sitting at the same voltage. So in other words, both the top node of P3 and P4, so the top node here has the same voltage for both these, both P3 and P4 have the same voltage on their positive poles and their negative poles. So they have to be sitting at the same voltage. But we know that P3 is sitting at 8 volts, right? It's given to us. And so P4 also has to be equal to 8 volts.
And it's is it 8 watts?
Yes, it's 8 watts. And the reason that you didn't actually need to do that to deduce that, notice that the sum of power has to be equal to 0, right? So we have negative 100 here, we have 60 here, and 48 here. And so before solving for P4, we have a net of, we have a net of,
8.
8. And so, oh, yeah, so we know that the answer here has to be -8, right?
Yep.
And so notice that this current is entering the negative end of this, this is the negative terminal and this is the positive. So we have the 1 amp that we got by multiplying 0.2 times 5 amps, and we got the 8 volts. But again, the current is exiting the positive end, so it has to be -8 watts. So, so then again, the for P4, we can just deduce that the value of -8 by applying the law of conservation of energy. So we cannot, the sum of powers, the sum of powers across the circuit has to equal to 0. And so there are 2 ways of getting to -8 here. Way number 1 is by noting that we know what the current is 0.2 times I, and we know what the voltage is because these 2 elements are set to be in parallel. And so we'll define what a parallel connection is in lecture 2. But for now, all that you need to know is that you just need to notice that P3 and P4 have the same connections at the top and at the bottom. One more problem. So here what I'll do is, again, this is one that I will do on the board, and I will move this out of the way. Here, I have an idea. And I'm going to annotate this one, try to make it a little bit more interactive. Okay. So let's start with P1 here, right? How do I, what two numbers do I have to multiply to determine the value of P1?
8 and 5.
5
5,
times -8.
Excellent, right? The current is going this way, and so this is, right, the 8 amps, right, is hitting the negative end. So we know that I'm just gonna, P1 is equal to 5 volts times -8 amps equal to -40 watts. Okay, so that's my answer for P1. What about P2? How do I compute?
Times 2.
Yeah,
2 times
exactly.
8.
Excellent. Okay, that's 16 watts. What about, let's do P3. So first of all, let's figure out, so this is a voltage source whose value is equal to 0.6 times I, where I is equal to 5. So how,
3
so what is
times 3.
Yeah, so 0.6 times 5 is what? Is
3.
3
Or we
volts,
could relate
right?
to P4 as well.
Yeah, so the voltage across this battery is 3 because 0.6 times 5. And this, the current flowing into it is oriented into the positive end. So the current, sorry, the power, P3, is equal to 3 volts times 3 amps is equal to 9 watts. Okay, so far we have a -40, a 16, and a 9. So then what does the value of P4 have to equal? Right, so power cannot be destroyed or created in a circuit.
It has to
15
equal,
watts.
What's that?
it has to equal 15.
Yeah, 15 watts, right? So it has, we know that it has to equal to
negative 40, or let me see, it has to equal, how do I write this? So we know that P4 plus, can I write like this? And therefore, P4 is equal to negative P1 minus P2 minus P3, which is equal to 40 minus 16 minus 9, 25 watts. And so that's one way of doing it. But another way of doing it is by noting that there's 5 amps flowing in, and there's a voltage of, and the 5 amps is hitting the positive terminal. And so another way of getting to this answer would be to multiply the voltage of 3 times the current of 5, which is 15 watts. Oops, this should be 15. Ah, and Zoom doesn't. All right, I'm gonna try to correct myself. I wrote 25 here, but it actually should be 15, but it's just a typo. It's not, the two answers are completely congruent. But I don't know how to, let me see. Okay, do it again. All right, so we have P1 plus P2 plus P3 plus 0, and therefore we have that P4 is equal to negative P1 15 watts. And then the second way of solving for P4 is to multiply the voltage by the current, making sure that the sign on the current matches our convention, which is that we indicate the current with a positive sign when the arrowhead is entering the positive terminal. So 3 volts times 5 amps is equal to 15 watts. Okay. So that that concludes. First of all, is there any questions on this problem? Okay. So Monday, you know, I have like an expiration period. After a certain amount of time of teaching, I just start to I start to tire. So even though we do have 2 hours and 45 minutes on Mondays, I will not always use the entire session time for the lecture, but I will try to balance, you know, the fact that it is not possible to pay attention, you know, consistently for, you know, really more than 90 minutes, I would say. And the fact that we do have to get through a large amount of material for this course. Okay, so I will wrap it up, and the link for the Wednesday lecture is different. So there's a Zoom link for the Monday lectures, and there's a Zoom link for the Wednesday lectures, and they are distinct. So on Wednesday, we'll use the second Zoom link, and we meet at 1 o'clock on Wednesdays on Zoom. So I look forward to continuing with the course content beginning on Wednesday with lecture 2. Have a good rest of your day.
Just a question. If you have a second. If you had to choose which chapters for the text would be relevant to these slides, which ones would those be?
Yeah, so it actually there's like a strict correspondence. I believe the first lecture is chapter 2.
Okay.
It's the one that, you know, if you just look at the content, like the lectures are very much kind of derived from textbook content. You know, this is a very standard introduction to electric circuits course.
So I believe it's chapter 2 though, that this first lecture corresponds to, but that's a good question.
Thank you.
You'll be able to know right away, no problem. All right, see everybody on Wednesday.